Welcome to this problem walkthrough. Today, we'll tackle the challenge of minimum remove to make valid parentheses, which is a fascinating string manipulation problem. We'll explore efficient approaches to ensure the resulting string is valid by removing the minimum number of parentheses. Let's dive in. The problem asks us to work with a string S that consists of lowercase English letters, as well as open and close parentheses. Our goal is to remove the minimum number of parentheses, whether they are opening or closing, to make the string valid. For a string to be valid, every open parenthesis must have a corresponding closing parenthesis, and any open parenthesis must appear before its matching close parenthesis. Importantly, while we are allowed to remove parentheses to achieve validity, all the lowercase letters in the string must remain untouched. Additionally, the guarantee of a unique solution means we don't have to worry about ambiguous outputs for a given input string. The output of this problem is a valid string that you obtain by removing the smallest possible number of parentheses from the input string. To clarify this with an example, consider the string S equals li, t, c, o, d. The output here is li, t, c, o, d. The explanation lies in the fact that the last closing parenthesis at index 13 is unmatched. Removing this parenthesis gives us a valid string where every remaining opening parenthesis has a matching closing parenthesis. In the case of the string S equals A, B, C, D, the output is A, B, C, D. Here, the closing parenthesis at index 2 is unmatched, and by removing it, we ensure that the string becomes valid. All other elements in the string, including the lowercase letters and the remaining balanced parentheses, are left untouched, maintaining the structure of the string while satisfying the validity criteria. Now let's look at the input S equals A, B, C. The output here is A, B, C. In this case, we have two unmatched parentheses, the closing parenthesis at index 0 and the opening parenthesis at index 6. Removing both of these parentheses results in a valid string where all remaining parentheses are balanced. Notice that all the other characters, including the lowercase letters, stay in their original positions in the output. The problem also comes with some constraints and edge cases to keep in mind. The string length s.length can range from 1 to 100,000, making it important to handle large inputs efficiently. Additionally, the string is guaranteed to contain only lowercase English letters, open parentheses, and closing parentheses. Edge cases include an empty input string, in which the output would also be an empty string since there are no parentheses to balance. Another edge case is when the string contains no parentheses at all, such as ABCDE, where the output remains the same as the input because no changes are needed. Finally, consider edge cases like a string with all unmatched parentheses, such as here, the output is an empty string because both parentheses are unmatched and need to be removed. On the other hand, if the input string is already valid, such as A, B, C, D, the output is identical to the input since no changes are necessary. These examples highlight the importance of carefully analyzing the input to determine the minimal changes required to make the string valid. When tackling the problem of removing the minimum number of parentheses to make a string valid, we considered several approaches. First, there is the brute force method, where we generate all possible substrings by removing parentheses and then validate each one. While this method is straightforward in concept, it is computationally prohibitive. Generating all substrings results in exponential growth, specifically O(2 to the power of n), and combined with the validation step, the total time complexity becomes O(n*2 to the power of n). This makes it impractical for any reasonably large input. Next, we have the two-pass string builder approach, which is more efficient. Here, we scan the string twice, once left to right to identify excess closing parentheses, and then right to left to identify excess opening ones. Using indices to track invalid parentheses allows us to construct the final valid string. This method has a linear time complexity of O(n), and avoids the exponential blowup of brute force. However, it requires managing additional data structures to store indices, which adds some complexity that can be avoided with a more streamlined solution. Another approach we considered is the stack-based method, which uses a stack to track unmatched parentheses. As we traverse the string, we push the indices of unmatched opening parentheses onto the stack. When we encounter a closing parenthesis, we check the stack. If it's not empty, we pop the stack to match the closing parenthesis with an opening one. Otherwise, we mark the closing parenthesis as invalid. After the traversal, any unmatched opening parentheses left in the stack are also deemed invalid. Finally, we construct the result string by skipping all indices marked as invalid. This approach is efficient, as it has a time complexity of O(n), with one traversal to process the string and another to build the result. However, the use of a stack introduces additional space overhead, making it less space efficient than simpler methods. While effective, we ultimately decided against this approach in favor of one that avoids extra data structures. The strategy we chose is a single-pass string builder approach, which is both optimal and clean. The key insight here is to directly build the result string while maintaining the balance of parentheses during traversal. A valid string must have balanced parentheses, meaning every opening parenthesis must have a corresponding closing one. During the first traversal, we skip any invalid closing parentheses as they are encountered, appending only valid characters to the result string. To handle excess opening parentheses, we perform a second traversal on the result string, this time from right to left, skipping any unmatched opening parentheses. This method achieves linear time complexity, O(n), with two simple passes over the string, and requires O(n) space for the final output string. It avoids the need for stacks or auxiliary data structures, making it elegant, efficient, and easy to implement. This simplicity and directness are the reasons we chose this approach. Each of the approaches we considered has its trade-offs. The brute force method, while conceptually simple, is computationally infeasible for larger inputs due to its exponential time complexity. The two-pass string builder is more efficient but requires managing indices to track invalid parentheses, which adds complexity. The stack-based approach is similarly effective but introduces additional space requirements due to the stack, making it less space efficient. The chosen strategy, the single-pass string builder, strikes the perfect balance between simplicity and efficiency. It minimizes the use of extra data structures, operates in linear time, and directly constructs the result string in a clean and straightforward manner. This makes it the cleanest and most practical solution for this problem, avoiding unnecessary complexity while maintaining optimal performance. The problem we are tackling involves making a string containing parentheses valid by removing the minimum number of parentheses. A string is valid if every open parenthesis has a matching closing parenthesis and they are properly nested. To solve this, we aim to identify the smallest set of parentheses to remove to achieve validity. Our approach will systematically generate substrings by removing parentheses and check which of these substrings are valid. For this, we'll use breadth-first search, or BFS, to explore all possible substrings, starting with the original string. We begin by initializing our BFS process with the original string. At each step, we generate new strings by removing one parenthesis at a time, either an open or closing parenthesis, from the current string. These new strings are added to a queue for exploration in subsequent steps. To ensure efficiency, we maintain a set to track which strings have already been visited, preventing redundant computation. Once we generate these strings, we validate each one using a helper function is valid. The validation involves traversing the string while maintaining a balance counter. This counter increments for each opening parenthesis and decrements for each closing parenthesis. If the balance ever becomes negative, it indicates an invalid string. At the end of traversal, the string is valid only if the balance equals 0. Additionally, we optimize our process by stopping further exploration at the BFS level where we first find valid strings. This guarantees that the strings found have the minimum number of parentheses removed. The choice of BFS as our traversal method is critical because it ensures that we explore strings with the fewest removals first, guaranteeing minimal changes to achieve validity. This strategy, combined with early termination once valid strings are located, saves unnecessary computation by avoiding exploration of deeper, less relevant levels of the BFS tree. Furthermore, the use of a set to track visited strings eliminates redundant processing, ensuring we do not revisit the same substring multiple times. To implement this solution, we rely on three key data structures: a queue for BFS traversal, a set to track visited strings, and a list to store the final valid strings. The pseudocode outlines the main structure of our algorithm, including the isValid function, which checks the balance of parentheses in a string. The isValid function starts by initializing a balance counter. As it traverses the string, it increments the balance for each open parenthesis and decrements it for each closing parenthesis. If at any point the balance drops below 0, the function returns false, as this indicates more closing parentheses than opening ones. If the traversal completes with a balance of 0, the string is valid. The BFS process continues by dequeuing strings for validation. If a dequeued string is valid, it is added to the list of valid strings, and further exploration for that level stops. Otherwise, new strings are generated by removing one parenthesis at a time from the current string. These new strings are checked against the visited set, and if they are unique, they are added to both the visited set and the BFS queue for further exploration. Finally, the BFS queue processes all unique substrings systematically, stopping early as soon as valid strings are found. The result is a collection of valid strings with the minimum number of parentheses removed. From a complexity standpoint, generating all possible substrings involves removing each parenthesis in the string. In the worst case, there could be up to 2 to the power of n substrings, where n is the length of the string. However, BFS optimizations ensure we stop early, reducing practical complexity. Checking validity for each string takes linear time relative to its length, leading to an overall time complexity of n*2 to the power of n. Space complexity is driven by the queue, visited set, and result list, resulting in an overall space complexity of n*2 to the power of n. This balances thoroughness with efficiency, making the algorithm scalable for moderately sized inputs. The provided code solves the LeetCode problem number 1249 minimum remove to make valid parentheses using a two-pass approach. Here's a detailed explanation. ### first pass, identifying invalid parentheses. 1. Stack initialization. The stack is used to track indices of unmatched opening parentheses. The to_remove set records indices of invalid parentheses, both unmatched and 2. Iterating through the string, as the code iterates over the characters of the string s. If it encounters an opening parenthesis, it stores its index in the stack. If it encounters a closing parenthesis. If the stack is not empty, it means there's a matching, so the top index is removed from the stack. If the stack is empty, it signifies an unmatched, so its index is added to _remove. 3. Unmatched. After processing the string, any remaining indices in the stack represent unmatched. These are added to _remove. ### second pass, constructing the result string. 1. Building the result. The second loop iterates over the string again, appending characters to the result list only if their indices are not in _remove. 2. Joining characters. The result list is converted back into a string using .join, result. ### efficiency. Time complexity, n, where n is the length of the string. The algorithm performs 2 linear passes over the string. Space complexity, n, due to the use of the stack, to_remove, and result data structures. This algorithm ensures that the minimum number of parentheses are removed to make the string valid, while preserving the order of non-parenthesis characters. Here, we start by importing the necessary libraries and defining our solution class. The goal is to identify and remove unmatched parentheses from the input string. To achieve this, we use a stack to store the indices of unmatched opening parentheses, and a set to track the indices of characters that need to be removed. The first loop iterates through the string, character by character. When we encounter an opening parenthesis, we push its index onto the stack. For closing parentheses, we check if the stack is not empty. If it isn't, we pop the top of the stack, since we've found a matching pair. However, if the stack is empty, it means this closing parenthesis is unmatched, so we add its index to the toRemove set. After finishing the loop, any indices still left in the stack correspond to unmatched opening parentheses, and we add those to the toRemove set as well. At this point, we have identified all the unmatched parentheses in the string. Now, we move on to constructing the final valid string. We initialize a string builder to efficiently build the result. Then, we iterate through the string once more, checking each character's index. If the index is not in the toRemove set, we append the character to the result. This ensures that only the valid parentheses and other characters are included in the output. Finally, we convert the string builder content to a string and return it. This approach ensures a clean and valid string with all unmatched parentheses removed, while maintaining the original order of the characters. To solve the problem, we start by identifying unmatched parentheses. For the input string s equals li, t, c, o, d, we initialize an empty stack to track the indices of unmatched opening parentheses and an empty set to underscore remove to store indices of unmatched closing parentheses. As we iterate through the string, we first encounter characters that are not parentheses, like L, E, and E. These are skipped, and the stack and to underscore remove remain unchanged. When we encounter an opening parenthesis at index 3, we add its index to the stack. This indicates that we have an unmatched opening parenthesis. We continue processing other characters, skipping non-parentheses, and adding the index of another opening parenthesis at index 5 to the stack. At index 7, we encounter a closing parenthesis, and since we have an unmatched opening parenthesis in the stack, we pop the top of the stack, resolving this match. For now, the stack still contains the unmatched opening parenthesis at index 3, while to underscore remove remains empty. As we continue, we process more characters like O, which are not parentheses, leaving the stack and to underscore remove unchanged. At index 9, we encounter another closing parenthesis. Since the stack has an unmatched opening parenthesis at index 3, we pop the stack again, resolving this match as well. Now, the stack is empty, meaning all opening parentheses so far have been matched. We continue iterating through the string, skipping characters like D and E. Finally, at index 12, we encounter an unmatched closing parenthesis, since the stack is empty. This index is added to underscore remove. Next, we handle any remaining unmatched opening parentheses. Since the stack is empty, no additional indices are added to underscore remove, leaving it as 12. In the second pass, we build the result string by iterating through the input string and including all characters except those at indices in to underscore remove. The result after this step is li, t, c, o, d. The final output for the first example is li, t, c, o, d. Now, let's move to the second example with the input string s equals a, b, c, d. Again, we start with an empty stack and an empty set to underscore remove. As we iterate through the string, we first process a, which is not a parenthesis, so we skip it. At index 1, we encounter a closing parenthesis. Since there is no unmatched opening parenthesis in the stack, this closing parenthesis is unmatched, so we add its index to underscore remove. We continue processing characters like B, skipping them as they are not parentheses. At index 3, we encounter an opening parenthesis, which we add to the stack. This indicates an unmatched opening parenthesis. Moving forward, we process C, skipping it, and at index 5, we encounter a closing parenthesis. Since the stack has an unmatched opening parenthesis at index 3, we pop the stack, resolving this match. The final character D is not a parenthesis, so it is simply skipped. After processing the entire string, the stack is empty, and the only index in to underscore remove is 1, corresponding to the unmatched closing parenthesis at index 1. Moving to the second pass, we iterate through the string to construct the result. We include all characters except those at indices in to underscore remove. This removes the unmatched closing parenthesis at index 1 while keeping the rest of the string intact. The result after this step is ab, c, d. The final output for the second example is ab, c, d. For the third example, the input is s equals a, b, c. As before, we start with an empty stack and an empty set to underscore remove. At index 0, we encounter a closing parenthesis. Since there is no unmatched opening parenthesis in the stack, this closing parenthesis is unmatched, so we add its index to underscore remove. We then process a, skipping it as it is not a parenthesis. At index 2, we encounter an opening parenthesis, which we add to the stack. This indicates an unmatched opening parenthesis. Next, we process B, skipping it, and at index 4, we encounter a closing parenthesis. Since the stack has an unmatched opening parenthesis at index 2, we pop the stack, resolving this match. Moving forward, we process C, skipping it, and at index 6, we encounter another closing parenthesis. The stack is empty at this point, so this closing parenthesis is unmatched, and we add its index to underscore remove. At the end of the first pass, to underscore remove contains the indices 0, 6, Since the stack is empty, there are no unmatched opening parentheses to handle, so to_remove remains 0, 6. In the second pass, we construct the result string by including all characters except those at indices in to_remove. This removes the unmatched closing parentheses at indices 0 and 6, while keeping the rest of the string intact. The result after this step is A, B, C. The final output for the third example is A, B, C. The time complexity of this algorithm is determined by the two passes we make over the input string. In the first pass, we iterate through the string character by character. Each time we encounter an opening parenthesis, we push its index onto a stack, which is an O1 operation. For closing parentheses, we either pop from the stack or add the index to the to_remove set, both of which are also O1 operations. Since we process each character exactly once, the time complexity of this pass is O(n), where n is the length of the string. In the second pass, we rebuild the result string by iterating through the string again and checking if each index is in the to_remove set. Set lookups and appending to the result list are average O(1) operations. This pass also requires O(n) time. Combining the two passes, the total time complexity of the algorithm is O(n). Now, let's analyze the space complexity, which depends on the additional data structures used. The first of these is the stack, which stores the indices of unmatched opening parentheses. In the worst-case scenario, where all characters in the string are opening parentheses, the stack will contain all n indices, using O(n) space. The second structure is the to_remove set, which holds the indices of unmatched parentheses. If all parentheses are unmatched, the set will also contain up to n indices, consuming O(n) space. Lastly, the result list is used to store the final valid string. Even in the best-case scenario where the input string is already valid, the result list will store all n characters, resulting in O(n) space usage. Therefore, each of these three structures contributes O(n) space, leading to an overall space complexity of O(n). Combining the contributions of the stack, the to_remove set, and the result list, the total space complexity of the algorithm is O(n). This is because each of these structures can grow proportionally to the size of the input string. When compared to a naive approach, which would repeatedly identify and remove unmatched parentheses, the current solution is far more efficient. A brute force method could involve multiple passes over the string, with each pass requiring O(n) time to identify unmatched parentheses and O(n) time to construct a new string. If there are k unmatched pairs, this would result in a time complexity of O(k*n). In contrast, the optimized solution achieves linear time complexity, O(n), by processing the string in just two passes and avoids repeatedly reconstructing the string. This makes it much more suitable for handling large input sizes. To better understand the algorithm's efficiency, let's look at the best, average, and worst-case scenarios. In the best case, if the input string is already valid, the stack and to_remove set remain empty. However, we still iterate through all n characters in both passes, resulting in O(n) time complexity and O(n) space complexity for the result list. In the average case, where most parentheses are balanced but a few are unmatched, the time complexity remains O(n), while the space complexity also remains O(n), due to the use of the stack, set, and result list. In the worst case, where all parentheses are unmatched, such as a string of consecutive opening or closing parentheses, the algorithm still processes the string in linear time and uses linear space for the auxiliary data structures. To summarize, the mathematical proof of the algorithm confirms that both passes together contribute O(n) time, and the use of the stack, set, and result list leads to O(n) space complexity. This ensures that the algorithm is efficient, scalable, and optimal for solving the problem. When solving this problem, there are some common mistakes to watch out for. First, failing to handle edge cases like empty strings or strings without any parentheses can lead to incorrect results. For example, if the input is ABC, it should simply return the same string because it's already valid. Another mistake is misidentifying valid parentheses. It's important to ensure that open and close parentheses are balanced, which can be done using either a stack-based or comp-based approach. Inefficiency is another common pitfall. Generating all possible substrings without eliminating invalid or redundant options can drastically increase runtime. Techniques like backtracking help prune unnecessary cases. Finally, overlooking duplicate results can waste computation time and produce incorrect outputs. Using a set to store results ensures you're only working with unique strings. Another frequent issue is not optimizing for the minimum number of removals. Generating all substrings without focusing on minimizing edits leads to inefficiency. Instead, approaches like BFS or DFS can help ensure you make the smallest number of changes. Now, in interviews, this problem often tests your ability to recognize patterns in parentheses validation, which is common in many string manipulation problems. Mastering stack-based in BFS or DFS approaches will give you an edge. Interviewers also look for optimization skills, so transitioning from brute force to more refined techniques is key. Don't forget to test on edge cases, such as empty strings, strings with no parentheses, or strings that are already valid. Finally, be prepared to discuss trade-offs between approaches, such as BFS, which guarantees minimal edits but uses more memory, versus DFS, which is more memory efficient but can explore less optimal paths. This problem is closely related to several other LeetCode problems. For example, LeetCode 20, valid parentheses, focuses on the foundational logic of validating parentheses using stacks, which is crucial for understanding this problem. LeetCode 22, generate parentheses, deals with generating all valid combinations of parentheses, helping you practice backtracking techniques. LeetCode 301, remove invalid parentheses, is a direct extension of this problem where BFS or DFS is used to generate all valid results. Lastly, LeetCode 32, longest valid parentheses, explores dynamic programming and stack-based techniques to analyze substrings, broadening your understanding of similar challenges. Now let's look at alternative approaches and their trade-offs. A brute force method involves generating all possible substrings, but this is highly inefficient, with exponential complexity of O(2 to the power of n, making it impractical for larger inputs. Backtracking is another approach that reduces unnecessary computations by pruning invalid cases early, but it can still be slow for large strings. Breadth-first search, or BFS, is effective because it guarantees the shortest sequence of removals, but it requires more memory to store intermediate states. On the other hand, depth-first search, or DFS, is more memory efficient but can end up exploring deeper invalid paths, which means additional checks may be needed to ensure optimality. Finally, stack-based validation is another valuable technique. While it's highly efficient for validating whether a string has balanced parentheses, it doesn't directly solve the removal problem. However, it's often used in combination with other methods to ensure accuracy and efficiency. By leveraging these approaches and understanding their trade-offs, you can tackle this problem and similar challenges effectively. That brings us to the end of this problem walkthrough. We learned how to effectively use a stack to solve the minimum remove to make valid parentheses problem with optimal time and space complexity. Remember, mastering these concepts will help you tackle similar challenges in interviews. Thanks for watching, and happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!